Hi everyone. In this section, we will talk about bit manipulation techniques, and these are nothing but these are some, maybe you can say, algorithms using which you can modify the data at their binary representation level. And every programming language provides us some bitwise operators which allow us to operate on the binary representation of the data that we have. Okay, so we will look how to use these bitwise operators, what are the different types of bitwise operators, and how we can use them to solve some problems. Okay, and the reason why we use bitwise operators sometimes is because they operate on the binary representation of the data, and they're fast as compared to if you use the non-bitwise operators. And what are the different types of operators you can see on the screen, and we are going to talk about and, or, XOR, one's complement, binary left shift, and binary right shift. Okay, so these are the bitwise operators, and if you're new to them, so let us explore each of them one by one. So the first one is a binary AND. So basically, let's say AND has very simple rules. Let's say you have two bits, one, and let's say the other bit is 0. So if you do AND with a 0, then it is going to give you a result of 0. Similarly, 0 and 1 is going to give you a result of 0, and only when both the bits are set, only then you will get a result of 1, and 0 and 0 is also going to be 0. So anything done an AND with 0 is going to give you a 0 bit. Okay, so these are the simple rules of doing a simple AND. And now what, how do we use it? Okay, let's say I have a number 5 and I do a AND with 7, then what I'm going to get? So let's see. So 5 in binary is represented as 000 followed by, let's say, 101, and it's a, let's say, 32 or a 64 bit number. 7 in binary can be represented as lots of zeros followed by 111. Now if you do AND, so it will happen on bit by bit level. Okay, so 1 and 1 is 1, 0 and 1 is 0, 1 and 1 is 1, and followed by lots of zeros. Okay, so if you convert this number back into the decimal, you will see this result is going to be 5. So this is how binary AND works. So I hope this is clear. And now let's see what is binary OR. So the rules of the OR are very simple. If one of the bits is 1, then the result is going to be 1. For example, 1 or 0 is going to give you, okay, so this is denoted using this operator. So 1 or 0 is going to give you 1. Similarly, 0 or 1 is going to give you 1. 0 or 0 is going to give you 0, and 1 or 1 is going to give you 1. So if one of the bits is 1, then the resulting bit would be 1. For example, if I do 5 or with 8, okay, so what is 5? 5 is 101. What is 8? 8 is 1000. Yes, and if you do a OR here, what you're going to get? You're going to get 1 here, 1 here, 0 here, and 1 here. So what is this number? This is 8, this is 4, this is 2, and this is 1. So if you add 8 plus 4 plus 1, so this number is actually 13. Okay, so these are actually powers of 2. So 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, and 2 raised to the power 3. So you can see I am doing 8 plus 4 plus 1, that is 13. Okay, so this number is actually 13. So if you do this in your code, you will get an output of 13 in this particular case. So I hope binary OR is also clear. And now let us move on to XOR. So XOR is also known as exclusive OR. Okay, exclusive OR. So what are the rules of XOR? So it basically means if both the bits are same, then the result is going to be 0. For example, 0 XOR 0 is 0, and also 1 XOR 0 is 1 XOR 1 is also 0. So if both the bits are same, the result is 0. Otherwise, if both the bits are different, then the result is 1. So if I show you, maybe if I do 5 XOR 7, so 5 is what? 5 is 0000101, and 7 is 00111. Now if I do a XOR here, then 1 XOR 1 is going to be 0, 0 XOR 1 is going to be 1, this is going to be 0 and lots of zeros. So this result is going to be 2. Okay, so if you do something like cout 5s or 7, then it is going to print 2 in your code. Okay, so I hope you understood this XOR operator as well. So the next that we are going to discuss is NOT. Okay, so the NOT is a very simple operator. So what it does, if I have a bit 0, okay, let's say this is not the integer 0, this is the bit 0. So if you do a NOT of 0, you're going to get 1. And suppose you do NOT of some number, okay, let's say you have a number like 000 101. Let's say this number is 5. If you do the NOT of 5, then it is going to flip all the bits. Okay, so NOT of 1 is 0, and NOT of this is going to be lots of ones followed by 0 1 0 1. Okay, so this, you will see, it is going to flip all the bits including the most significant bit, that is the sign bit. Okay, that is the sign bit. So that means this number could be a negative number as well. Okay, now if you have little idea here, I can give you one example. Let's say I take something like this. Let's say I take int a, and I say int a is 0, and I simply do cout not of a. Then what you're going to expect? Okay, what would be the answer? The answer is going to be actually not 1, but it would be -1. Okay, now you may wonder why it is so. So if you look 0 at the memory level, so what is 0? So 0 is a 32-bit number in which everything is 0. All the 32 bits are 0. So if you do a NOT of it, you will get all 32 bits as ones. Okay, and all 32 bits are ones, and the most significant bit represents the sign bit. Okay, so if this sign bit is 1, that means it is a negative number. So that means it is a negative number, and the remaining 31 bits, they represent the magnitude. Okay, now for the negative numbers, if we want to find out the magnitude of that particular number, so these numbers are stored in a form known as 2's complement form. Okay, they're stored in a 2's complement form. So in order to find out what number is this, what we need to do, we need to take the 2's complement, that means invert all the bits and add 1 to it. Okay, so the number is this. In order to find the magnitude, we have to first invert all the bits. If I invert all the bits, it becomes like this, and then I will add 1 to it. So this number is 0000001. So basically this is a negative number with a magnitude of 1, hence this number is actually -1. Okay, so if you do NOT of 0, and where 0 is an integer, you are going to get -1 as an output. Okay, and NOT of 0, where 0 is a bit, it would be 1. Okay, so that is something that you should be very careful while working on. Okay, so this something you can try it on your own as well. Okay, if you don't trust me, I am going to show you the demo as well. So I have this code where I have x is 0 and I'm doing cout not of x. So let us run this code and see what we get as an output. This should be /bitwise. So you can see this output is actually -1. That is because of the same reason I have discussed. Okay, so doing a negation of all zeros gives us a number in which all numbers are ones, and since it is stored as a 2's complement form, the first bit denotes the sign bit, the remaining bits denote the magnitude, and in order to find the exact magnitude, we have to take 2's complement. So this process is known as 2's complement, where we invert all the bits and add 1 to it, and whatever you get, this number, this is the magnitude of the number. Okay, so if you convert this number into decimal, this number is 1, and sign is -1 because the most significant bit is 1. Okay, so I hope this is clear, and now you understand that doing a negation of a bit 0 is 1, and doing a negation of an integer 0 is -1. It's an important concept, so I have explained it to you. So binary NOT is clear. Now we will talk about two more operators, left shift and right shift, in the next lecture. Hi everyone. Now we are going to talk about binary left shift. So what is this operator? So generally you will find this operator written like this. Let's say 5 left shift 2. So what does it mean? So it basically means we have a number 5, okay, and whatever is the bits it has, we are going to left shift all the bits by a factor of 2. So everything is going to move towards left by a factor of 2. So what will happen? These two bits will fall off, okay, and you will have something like this: 0 0 1 0 1, and from here you will add two zeros, okay. So you will add like this. Now if you try to understand what is the difference in this number, so this was 2 raised to the power 0, this was 2 raised to the power 1, this was 2 raised to the power 2, and here it is 2 raised to the power 0, 2 raised to the power 1, and this is 2 raised to the power 2, this is 2 raised to the power 3, and this is 2 raised to the power 4. So what is the original number? So original number is 5, okay, and that is equal to 2 square plus 2 raised to the power 0, and we know this is 5, and let us call this number as x. Now if I talk about this number, okay, so what is this number? So it is nothing but it is 2 square plus 2 4. So if you take 2 square common, what you're left with? You're left with 2 square plus 2 raised to the power 0. So that means it is 2 square of the original number x. Basically, doing a left shift by 2 has multiplied that number by 2 square, okay. So basically a left shift b will multiply a with 2 raised to the power b. This is what I'm trying to say. And if you see, what is this number? This number is nothing but 16 plus 4, this number is 20. So effectively 5 got multiplied by 2 raised to the power 2, that is 5 into 4, that is 20. So effectively when you do a left shift, the number is multiplied with the power of 2. So this is the left shift operator. I hope this one is now clear. Similarly, we also have something known as right shift. So left shift does multiplication, right shift divides, okay. Let us start with a one example. Let's say I have a number 10, and if I do a right shift with 1, that means I'm going to divide by 2 raised to the power 1, okay. So if I show you this number, so 10 in binary is 1010, and that means if this is the number, doing a right shift means we are moving every bit towards right by one step. So this bit will get discarded and the original number would become 000101, okay. And clearly we know this number is 5. So if we do 10 right shift 1, that means divide by 10 divided by 2 raised to the power 1. So this number is 5 and this number is also 5. Again, if you do a right shift 1 here, it's an odd number, you should get 2. So this doing right shift 1 here means 000. This 1 will fall off and we will get something like this 10. So this number is 2. So this is same as doing 5 divided by 2 raised to the power 1, that is 2, okay. And similarly if you do it once again, you will end up getting 0001, and this number is 1. And let's do it once more, you will do 0000, this number would be 0. So if I do 10 right shift 4, then that means 10 divided by 2 raised to the power 4, and that is 16. So this number would be 0, okay. So a right shift b basically means a divided by 2 raised to the power b, okay. So I hope both left shift and right shift are now clear to you, and in the coming lectures we will see some examples where these operators can be used. That's all for this lecture. Thank you. Hi everyone. Now we are going to look at very small example of a bitwise operator. So we need to write a function to check whether a number is odd or even, okay. So not even a function, even we can write a small expression to check whether a number is odd or even, okay. So one thing you might know is we can simply do n modulus 2. If this gives us 0, then we can say the number is even. If it gives us 1, the number is odd, okay. But since we are learning about bitwise operators, we want to solve this problem using a bitwise operator. So one thing you will observe is all the odd numbers will have the last bit as 1, and all the even numbers will have last bit as 0. Okay, so I'm writing for, so this number is 1, this number is 2, this number is 3, this number is 4, this number is 5. One thing you can clearly observe is, for odd numbers, the last bit is 1, and it contributes 2 raised to the power 0, that is 1, to the answer, and that is what it makes the number odd. Okay, so everything else is a even number. Okay, everything else is a even number. That means the last bit decides whether the number would be odd or it would be even. So what we need to do, we need to check if last bit is 1 or it is not. Okay, so what we can do is, let's say we have some number 0 0 0 1 0 1 0 1 1. What we can do, we can do the AND with this one. Okay, so what is this one? This one is nothing but 0 0 0 0 0 0 0 0 and 1. If you do an AND here, and what could be a possibility doing an AND, so we have lots of zeros here, the only thing we will get is at the last position. So if the last position is 1, that means this position was 1. Okay, and that means this number is odd. But suppose the last position, if it is 0, then we will get a 0 here. That means this number is actually even. Okay, so I hope you understood how we can check whether a number is odd or even. So let me show you a quick demo in the code as well. So if I have let's say this code, I can simply put a if else. So int x, scene x, I can check if x and 1, I can see out odd, else I can see out. So dot slash odd. So if I give 5, so 5 is odd. If I give 8, 8 is even. If I give 32, it's odd, it's even. If I give 33, it's odd. Okay, so 32 is even, 33 is odd. So I hope now you understood how we can use this and 1 to find out the last bit. Okay, and that's it for this lecture. So thank you for watching. Bye bye. Hi everyone, in this lecture we will talk about some common operations that we can do using bitwise operators. So let us look at some examples. Let's say we want to get the ith bit of a number. Okay, for example, let's say the number is 5, and in binary it would look something like this: 0 0 1 0 1, and the numbering of bits that I'm going to do is from the right. So this is the 0th bit, this is the first bit, this is the second bit, and so on. If I say okay, give me the second bit, then I'm talking about this bit. I want to check the value of this particular bit. Okay, similarly there would be a function like set ith bit or update ith bit, then clear ith bit, then clear a range of bits. So we are going to see multiple functions in this set of lectures. So let us start with the first one. I want to get the ith bit of a number n. So now you may ask, okay, how we can extract that bit? So it's going to be pretty easy. Let's say if int n is 5, and the position of the bit, that is I, that I'm going to take input. Okay, and we will print the ith bit of the number. Okay, so now let's see how we can do it. So we know we can use bitwise operators, but how? So if I do something like this, if I have, let's say 101, okay, and I actually want to extract this particular bit. So we have seen how to get the last bit. Okay, so we basically do with the AND with a 1, but doing a AND with 1 will not help us in this case. So what we want, we actually want a variable in which we have we have 1 at this particular location and everything else is going to be 0. So if I put everything else as 0, then I will get this number. And how do I get this number? So it is nothing but it is 1 left shift I. So if you left shift 1 I times, okay, so I is 2, okay, and we are talking about 0 1 2, we are talking about this bit. So 1 left shift 2 basically means this number 1 0 0, which is this. And if you do a AND here, what you are going to get, you are going to get a number 0 0 0 1 0 0, okay, because everything else is 0, so doing an AND will convert everything else into 0. And for this position, since you have a 1 here, so doing a AND with 1 will give you this number. Now you can check if this number is greater than 0, that means the bit is 1. And if this number is equal to 0, okay, which would happen if this bit is 0, then you can say this bit is actually 0. So what we need to do, we need to create a small variable, let's say mask. Okay, I'm calling this number as a mask, and we will do the AND with the mask. Okay, so mask is nothing but 1 left shift I, and I can say the last bit is nothing but the number and mask. Okay, if I do the and if it gives me a result which is greater than 0, then I can return 1, otherwise I can return 0, and this is going to give me the ith bit. So let's run the code and see. So if I do dot slash common operations, so I say, okay, tell me the second bit of 5, so it is 1. Tell me the first bit, it is 0. Tell me about the 0th bit, it is 1. So that means it is working fine. So that's all for this lecture. See you in the next video. Hi everyone. So now we are going to look at how we can clear the ith bit. Okay. So basically, if we have a number like, let's say 1101, and I want to delete this bit and I want to make it 0. Okay, I want to clear the ith bit. So I is 2 for this example, let's say. So what I need to do, I need to create a number in which only this bit is 0, and rest everything else is going to be 1. So I need this as 0 and rest everything is 1. Okay, so can you guess how we can get this particular kind of a number? Okay, so one thing we know is the ith, we want to work on the ith bit, so we can create a mask using 1 left shift I. So it will give us something like this 0 1 0 0. Okay, that is fine. And how do we get this number? So it is nothing but it's a knot of this number, so bitwise knot. So what we need to do, we need to do a negation here, and once we are getting this, what we can do, we can do AND. If we do an AND, all these bits will be preserved, so we will get 1 0 1, and since we have a 0 here, so 0 and something, it is going to get 0. So that's it. So this is going to clear the ith bit. So if I show you the mask now, the mask is going to be nothing but knot of 1 left shift I, and what you need to do, you need to update the value of n. So you need to say n equals to n and mask, and we are done. So instead of calling set ith bit, I'm going to call clear ith bit. I give n and I, and let us clear the, so this number is what, 1 2 4 8. This number is 13. So if I say, let's say n is 13 and I want to clear the second bit. If n is 13 and I want to clear the second bit, I should get a number which is 9 0 1 2. Yes. So let's see. So I want to clear the second bit. Okay, I need to run this code, build this code first. If I clear the second bit, I'm getting an output which is exactly equal to 9. Okay, so I hope this is clear to you, and this is how we can clear any bit in a number. Hi everyone, the next thing that we are going to look at is how do we set ith bit. Okay, so we need to write a function void set ith bit, and we get a number and we get the position. So one thing you can do is you can take this number by reference and you can change the value here, or you can return the new number. Okay, so maybe another way to make this function is like this. Okay, and here you have to return the new value. So maybe I want to go with the first one because we want to change the value of n in the function itself. So let's see how we can do it. So it's actually very easy, very similar to what we have seen in the get. Let's say the number is 5 and I want to set the first bit. Okay, so I want to set the first bit, that is this one. Okay, so what I need to do a OR operation, a bitwise OR, with a number which looks like this, 0 1 0, which has a set bit at the ith index. Okay, and ith bit should be set. So what we need to do, we need to create a mask, that is, again, this number is going to be 1 left shift I. So we'll get this number and we will do a bitwise OR with the value of n. So let's see. So we can say int mask equals 1 left shift I, and what we can say, let's update the value of n as n or mask, and we are done. Now if the number is 5, if I say okay, get ith bit, okay, I can say void, I can say set ith bit. Instead of calling this, I can call set ith bit. I give the value of n and I, and maybe I print the new value of n. So let's try to run this. So I say okay, let us set the first bit. So you can see after setting the first bit, the result is 7, which is fine. If I set the 0th bit, then the result will not change because that bit is already set in 5. So that's all. That's how it is going to work. So we are getting this number 111 by setting the ith bit as 1. That's it. See you in the next lecture. Hi everyone. So now we are going to discuss one more method that we need to complete, update ith bit. Okay, so what we will get n, the position and the value that we want to put in a particular bit position. So let's say we have a number like this and I say okay, this is the ith index and I want to update this index as 0. Okay, so what I need to do, I need to put this as a 0, or it may happen that okay, no, this is the ith index, I want to put this index as 1. So we need to write a code such that it handles both the cases. Okay, so one way of doing this is what we can do, we can create a mask. Okay, we can create a mask and we know how to set this particular bit to 1. Okay, that is something we have already seen. But suppose if this bit is 1, I want to set it to 0. Okay, that we have also seen. So basically we need to combine the functionality of set bit plus clear bit in this particular case. Okay, so what we can do is, let's say we are talking about a particular bit position 1 1 1 0 0 1 0, something like this. I want to do some work here. So first what I can do, I can just clear this bit, I can make it 0. Okay, I can destroy this bit, that means I will make it 0, and once this bit is 0, we can actually do a OR operation with the mask. Okay, the mask would look something like this. If I want to, if the value of bit that we want to set should be 1, or the mask would look something like this, all zeros, if the value that we want to set is going to be 0. So if you do the OR, you will have the right bit here. Okay, you will have the updated bit, and rest all the bits will remain same. Okay, rest everything will remain same. So here you will get the right value. So basically if the value is 0, we just need to do the clearing part, and if the value is 1, we first need to clear that bit so that it handles both the cases. Whether the old bit was 1 or 0, it will work for both. So what I can do, I can simply call clear ith bit, I can give n and I, and once it is done, what we can do, we can create a mask which is like this. I can say okay, int mask, that is equal to 1 left shift I, and we can return, okay, it's a update method, so we can pass it by reference. So we can say n equals to n or mask. That's it. This actually sets the right value. Okay, and sorry, this should not be 1 left shift I, this should be value left shift I. Okay, so that is v left shift I. So if the v is 0, okay, if the v is 0, this will be entirely 0, and doing OR with 0 will not do anything. Okay, and if v is 1, then this number would be something like this, and this will create the right mask for us, and the ith bit would be set in the value of n. So let us try to do some work. Maybe I can call this method update ith bit and endl. So let's say the original number was 13, and I can say ni and value. Let's say I want to set some bit in 13 to 1. So let me show it to you. Okay, so I want to set, so 13 is 1101, so I want to set the first bit as 1. Let me build the code. Okay, so 13 was like this, 1101. So if I set the first bit, then this number becomes 1111, which is 15. That is fine. If I say no, I want to update the second bit and I want to make the value as 0. So let's see what happens. So I want to say, okay, set this bit as 0 and take I as input from the user. So second bit should be 0. Then the number would become, if this is set to 0, it would become 1001, and this number is nothing but 9. So I hope update bit is clear to you, and this is how we can implement update ith bit. Hi everyone, so now we are going to discuss one more method that we are going to write. So we want to clear the last I bits. So we are given a number n, and we want to remove all the last I bits of that particular number. For example, if we have a number 1110010, and if I say okay, I is 5, that means we will remove the bits from 0 1 2 3 4. All these bits should be made to 0. Okay, so we want to convert them to 0, and this should be the resulting number. This is what is expected from the function. Now how we can do it? So clearly what we can think of is, we actually need a number of this form in which these 3 bits are set and rest everything is set to 0. Okay, and it may happen we may also have something like 1 0 here, then this should remain intact. Okay, so the mask would be like this. So we want to create a mask in which the last I positions are 0, and once we create this mask, what we need to do, AND of these two numbers to get this as a result. Now how do we create this mask? Okay, so it's going to be quite easy. So what if I tell you, if you have a number in which you have all ones, okay, and then if you left shift it with I, what you will get? You will get I number of zeros in the right. Okay, so basically you will get a number like 1111 followed by I number of zeros, and this is what we exactly need. This is what we need. Starting from the index I plus 1 till the 0th index, we need everything as 0. So we have already seen, if you have this kind of a number, now what is this number in binary? Okay, how do we represent this number as an integer? So this number can be represented in using two ways. One is it can be represented as not of 0, because if you talk about 0, 0 has all bits as 0, and not of 0 has all bits as 1s. And we also said that this number represents -1. So either you take -1 or you take not of 0, both are going to remain same. And what you need to do, you need to do the left shift of -1 with I, and then do a AND with your original number. Okay, so this is what we need to do. So I can say int mask is nothing but let's say -1 left shift I, that's it, and the number would be n and mask. That's it, and our work is done. So maybe let's say n is 15 and let's say I is 2. I don't take input. If I remove the last 2 bits of 15, let's see what we should get. So 15 is like this, 1111. So we are saying, okay, let us clear the last two bits. So it should be 1100. So it should be 12. We should be getting an output as 12. So instead of calling this method, we can call clear last I bits. I give n and I. That's it. Okay, this should be void. And yes, we are getting the output as 12. So I hope this functionality is clear. In the next lecture, we'll discuss one more. Hi everyone. So now we are going to discuss one more function that is bit tricky than what we have done so far. And so what we need to do, we need to clear bits in the range I to j. So what we are given a number, maybe something like this, 1100100110, and let's say I'm given index I and index j. I want to clear all the bits in this particular range. Okay, let's say this is I, this is, let's say, j, and this is I. Okay, so I want to remove all the bits starting from index, sorry, I want to, yes, I want to remove all the bits starting from index I till the index j. So they need to be cleared out. I want to set them as 0. So we have seen, if you need to clear a particular bit, you need a mask in which we have 0 at that particular index. So for this case, what we need is, we need a mask in which we have all the bits at these position as 1, and all the bits at this position as 0, and all the bits at the positions starting from I plus 1 till the 0 as 1. Okay, so we need something like this. Okay, this index is I, this index is j, these bits should be 0. So we need to see how we can create this particular kind of a mask. So the thing is very simple. We can actually break this down into two components. How to create this mask? Let's say this one part is a, and a looks something like this. We have lots of ones followed by all zeros, and we can also have b, in which we have lots of zeros followed by ones starting from the index I plus 1. Okay, this is something we can actually do, and this is what we have. We have j number of we have j plus 1 number of zeros here. Okay, so basically, in order to create this mask, we have already seen what we can do. We can take all ones, and we can right shift it with j plus 1. Okay, so if we have all number of ones, okay, that is nothing but that is not of 0, or that is minus 1. So if we do a left shift with index j plus 1, we will get the number a. Okay, that's it. How do we get a number b? So finding the number b is, you can find that this number is nothing but, if you look at a number 15. So what is 15? 15 is lots of zeros followed by 4 ones. What about 31? This is lots of zeros followed by 5 number of ones. We need something like this. So this number is of the form 2 raised to the power n minus 1. And what is 2 raised to the power n? So for 15 we get 4 bits. Okay, so if n is 4, we get last 4 bits as 4. So how many bits we need here? We actually need I number of bits here. Okay, we actually need, so this is from 0 to I minus 1. We actually need I number of bits here. Okay, so basically it is nothing but, this number is nothing but 2 raised to the power I minus 1. And what is 2 raised to the power I? So we can write this as 1 left shift I and subtract 1 out of it. So b is nothing but 1 left shift I and subtract 1 out of it. And what is mask? Mask is nothing but a or b. So now we get this number, and what is our final number? So mask we now have, and what is the value of n? So if you do a AND of this mask with the number, it is going to clear these bits from I index till j. So n is going to be n and mask. That's it, and we are done. Okay, and we are done for the method. So let's try to implement the code and then we will see in the output. So let us first find out a. So a is nothing but not of 0 or -1, you can take. Left shift j plus 1. Okay, and what about b? B is 1 left shift I -1. And what is mask? It is nothing but a or b. And what is n? N equals to n and mask. That's it. So let us say our n is 31 and I want to clear the bits in the range, uh, let's say 1. I is 1 and j is, let's say, 3. Okay, so I can say clear bits in the range. I give the number n, I give I, and I give j, and let us see what output it produces. So it is giving us the number 17. So let's see what happens. So 31 is 5 times 1 and 0, 1, 2, 3. So I said okay, clear all these 3 bits. So I get the number 1001. This is nothing but 2 raised to the power 4 and this is 2 raised to the power 0. This is 16 plus 1, 17. And we are getting this number 17. That's it. That means the code is working perfectly fine, and I hope this is clear to you. Hi everyone. So now we'll solve a very interesting problem using the concepts that we have learned so far. So what I'm going to do, I'm going to explain you the question. The question is very simple. It says we are given two 32-bit numbers n and m, and we are also given 2-bit positions I and j. So we need to write a method to set all the bits between I and j in n equal to m. So let me give you one example also. So if you look at this, this is what n is given, this is what m is given. So what I want is I want to put m inside n from index uh, j to I. Okay, so starting from index j till the index I want to put all the bits of n which should be same as m. Okay, this is what we need to do. So let me try to show it to you. So we have n 1 followed by, let's say, 10 zeros. Okay, and indices is 2 and 6. So basically it is like this: 0, 1, 2, 3, 4, 5, 6. I want to replace these bits with the bits from m. So the bits from m are 1, 0, 1, 0, 1. Okay, so basically these bits may also have 1 or they may also have something else as well. I don't know. But what I want is, if I want to replace these bits with this, so first I need to clear these bits. Okay, so first I need to clear the bits from index j to I, and for that we have already implemented one function in one of the lectures. So we can first call that function clear bits j to I, and once we have that, what we can do, we can do an OR with m, but m should also have these number of zeros here. Okay, that means m should be left shifted by a factor of I. So what we need to do, we need to create left shift m by a factor of I, and we need to clear the bits in n, and once we are done that, we can do the OR operation of n in which these bits are already set to 0 with m which has been shifted to the right index, and then we will get the right result. Okay, so that's it. That's what we need to do. So if I give you this example now, you can see the output is like this. So I will first copy this function clear bits in the range j to I. I will paste it here, and let me just comment out the problem statement. And now what we need to do, we need to create this method void replace bits. I have n, I have I have j, I have m. So what we need to do, first we need to call the clear bits in range method. I give n, I and j, and then we need to create a mask. Okay, so mask is nothing but m left shift I, And finally we need to return, or we need to say n equals to n or mask. That's it, and we are done. Okay, so let us look at one example. Let's say n is 15, I is 1, j is 3, j is 3, and m is 2. So if I say okay, replace bits n, I, j and m, and if I do cout n now, I should see some output. Let us try to build this code and let us try to run it. So this is, so I'm getting an answer 5. So let's see what we have done. So we have n, which is 15, so it is 1 1 1 1. We have I and j, so this is 0 1 2 3. I said okay, replace these bits with bits of 2. So what is 2? 2 is 1 0. Okay, so 2 is 0 1 0, and this is what we are going to get. Okay, now if you see, these bits are replaced. So what we did, we first cleared these bits, we made this number as 0001, then we left shifted 2 by a factor of I. So 2 by doing a left shift of I becomes like this, and then we do a OR operation, so it becomes 0101, which is equal to 5. That means our code is working as expected, and we are done. So that's it for this lecture. Thank you. Hi everyone. In this lecture, I will teach you an interesting property. How you can check whether a number is a power of 2 or not. Okay, and we will use bitwise operators to do this check. So let us talk about a power of 2. Let's say 16 is a number which is a power of 2, or 8 is a number which is a power of 2. So what is 16? 16 in binary looks like this. Yes. And what I can do is this, let's say this number is n. So can you tell me what would be n minus 1? So clearly we know the n minus 1 would be something like this, if n is a power of 2. Okay, so we know if n is a power of 2, then the previous number would look something like this. So this number is actually 15. And an interesting property is, if n is a power of 2, then doing a AND of these two will always give me a 0. Okay, and you can see this number is 0. Similarly, it is true for 8 and 7 as well. So if 8 is like this, then 7 is like this, and if you do a AND here of 8 and 7, then you will get a number 0. But this will not be true for any other number. For example, 5 is 101. What is 4? So 4 is 100, and if you do a AND here, you will not get a 0 here. Okay, so basically the check is, if you get something like this, if n and n minus 1, if they produce a result that is equal to 0, then that means n is a power of 2. Okay, so simply what we can do in the code, we can take input n, and I can check if n and n minus 1, and I maybe put a bracket here. If this is equal to 0, then you can say cout yes, power of 2, else you can say not a power of 2. Okay, so let's build it, run it, and check it quickly. So 128, yes, it is a power of 2. 144, it's not a power of 2. Okay, and 1024 is a power of 2, and 12, it's not a power of 2. So yes, it's working fine. So it's a order 1 check without doing anything. With just this AND operation with n minus 1, we can tell whether a number is power of 2 or not. That's it for this lecture. Thank you. Hi everyone. So in this lecture, we will see how you can count the number of set bits in a particular number. So what are set bits? Set bits are those bits which are 1. For example, if I give you the number 9, which is like 1001, then I can say it has 2 bits which are set bits. So I want to count the number of set bits in the binary representation of any number. That's what we need to do. So let us see how we can approach this particular problem of counting set bits. So let us discuss the approach. So it's pretty easy. So we know the number is stored like this, and we also know how we can find out the last bit. So we can do a AND with 1, and this will tell us what is the last bit. We will get to know, okay, this bit is 1, and for the next iteration what we can do, we can remove this bit by doing a right shift. Okay, so we can say the last bit is n and 1, and if this bit is 1, then I will increment the count of my set bits. If it is 0, I will not increment the count. Okay, or I can simply write, let's say initial count is 0, then I can say count plus equals to n and 1. So if the last bit is 1, then count will increment by 1. If the last bit is 0, the count will increment by 0. And I want to remove this, so I can say n equal to n right shift 1. Okay, so next time you will get 1 and 0, it will be 0, count will change by 0. Next time it would be, you remove this one, 0 and 1, it would be still 0, so count will change by 0. Next time you remove this 1 and 1, it is 1, so count will increment by 1, so final count would be 2. Okay, so this is what we can do. So I can write a function count bits, I get the number n, and here I can say while n is greater than 0, what I can do, every time find out the last bit. So I can say int last bit, I don't know, or maybe I can say int count, that is 0, and here I can find out the last bit. So last bit is nothing but n and 1, and I can say count plus equals to last bit. Okay, if it is 1, count will change by 1. If it is 0, count will not change. And then we can do is n equals n right shift 1, and from here we can return the count. So here we go. So what I can say, int n scene n, and I can say cout count bits of n. That's it. And I hope this is now clear to you. And what we are doing is, we are doing a very simple operation. Every time we are doing a right shift, okay, so we do a AND here, this goes off, next time these two bits interact, okay, and finally we will get a 1 here. So this 1 is added to the count. So this we will do for all the bits, and for a number n, the at most the number of set bits is going to be log of n. Okay, so the number of times this loop is going to run, it is going to run at most log of n times for a number n, because a number n has log of n bits. That you can easily verify by taking some examples also. Let's say 16 is like this. So 16 has, like, it's like 2 raised to the power 4. It would have at most 4 plus 1, that is 5 bits. Okay, talk about 7. So it's going to be around 2 raised to the power 3. So 7 is going to have at most 3 bits. So log of 7 is close to 3. Log of 16 is close to 4. So that's what I'm trying to say. So for any number n, you have at most log n bits. And okay, count is not declared, so this should be cnt. And yes, we are done. And now we can actually run our code and see. So dot slash count bits, if I give 16 has only 1 bit. If I give 15 has 4 set bits. If I give 8 has also 1 set bit. So that's all for this lecture. Thank you. Hi everyone, in this lecture I'm going to discuss a hack to count the number of set bits. So first I will show you the code, then I will tell you why this code works. So what we are going to do, we want to count the number of set bits, and I have the number n. So what I will do, I will say, okay, the number of bits is, let's say, answer, that is 0, and while n is greater than 0, I'm going to do one operation, that is the main part of this method. I'm going to do n and n minus 1, and I'm going to do answer plus plus. Okay, so what we are going to do, we are going to count how many times this loop is going to run. So basically what this operation does, it actually removes the last set bit from the current number. Okay, and we are going to return the answer. So let me give you one example. Let's say n is 9, and 9 in binary is like 1001. So what I'm doing, I'm updating n as 9 and 8. So if you do and with 8, so what is 8? 8 is 100. Okay, and what is going to happen is, after doing this and, what you will get? You will get this bit will become 0. Basically this bit will get removed and you will get 1000. And again we are going to do the same work. Now the value of n is 8 and we are going to do an and with 7. So and is 7 is what? This is what is 7. So if you do an and here, you will get the number 0. So that means in just 2 iterations we made this number 0. And what happened is, in the first iteration this bit got removed, in the next iteration this bit got removed, because we are removing this bit here. Okay, so every time we are going to execute n equal to n and n minus 1, it is going to remove the last set bit from the current number. Okay, so if a number has, let's say, bits like this 1 1 0 0 1 0 1, in the first iteration it will get removed, in the next iteration it will get removed, in the next iteration it will get removed, in the next iteration it will get removed, and the number would become 0. Okay, so if you go with the first method, you would have been iterating 1 2 3 4 5 6 times. But if you go with this method, it will just take the number of iterations that is equal to the number of set bits. Now I think with this example it is clear to you why this method is going to work. And let us also test our functionality. I can call both the functions. I can call count bits hack and I give n here, and if I run this code now, we can see, if I talk about 15 has 4 bits. In this case, the number of set bits and the total bits is 4, so both the methods are going to take the same number of iterations. But if I do it for, let's say, 16, then the second method will just run for one time, because we are counting the number of iterations and that is equal to answer. Okay, so that means in just one iteration it could tell that 16 has only one set bit. And maybe we do it for 9, so 9 has 2 set bits. Both methods are working as expected. So that's all for this lecture. Hi everyone, in this lecture we are going to discuss how we can convert a decimal number into its binary representation using the bitwise operators. Okay, so what I'm going to do, I'm going to write a method int convert to binary, and I'm going to get an integer, and let's say the integer is 9. So I will return a number which looks like 1001. Okay, so I'm also going to store this in a form of a integer. Now let's see how we can solve this problem. So it's easy. What we need to do is, let's say this is the number and we know how to extract the last bit every time. So we'll extract this bit and we'll create an answer variable. Okay, so the answer is initially 0. We will add 1 to it. It will become 1. Okay, and next time we are going to discard this bit by doing a right shift, n equal to n right shift 1. And we are also going to maintain a power. So power is initially 1. So we'll multiply 1 with 1 and add to the answer. Okay, so this is actually 1 into 1. Now next time, this is actually 10 raised to the power 0. This is 10 raised to the power 1. This is 10 square and this is 10 cube. So what we are going to do, we are going to generate the powers of 10. In the next iteration, this power would become 10. And we see this bit is 0. Okay, so if this is 0, what we will do? We will do 0 into 10. So the answer is not going to change. But we are going to discard this and we are going to go here and the power would become 10 square. So next time we get this bit, this is 0. So multiply with 10 square, this is 0. So the answer is not going to change. It is still 1. But next time what is going to happen, we discard this, the power is going to become 10 cube. And we see this bit is 1. Okay, so this bit is 1. So basically we can say for this bit we want to add 1000 to our answer. So we will add 1 into 10 raised to the power 3. So if you see what would be your final answer, it would be 1 plus 10 raised to the power 3. That is, it's going to be 1001. And this is how the binary representation of 9 would look like. Okay, so I hope you understood the logic now and try to code it yourself. And if you're stuck, then take the help from this tutorial. So what I'm going to do, I'm going to take input n and I'm going to convert it into binary. Okay, and what I can do, I can say initially the answer is 0, the power is 1, and while this n is greater than 0, I'm going to extract the last bit, that is n and 1, and I'm going to add something to my answer. So answer would be incremented by a value of power into last bit, and for the next iteration power will be multiplied with the 10. So initially it is 1, then it is 10, then 10 square, and then 10 cube, and n would be updated as a n right shift 1. That's it, and we are done. And from here we can return the answer. Let's build the code. So we can just see out convert to binary, and we give the input n here. And now let us test our code whether it works fine or not. So what we need to do is go to the terminal, and I can say convert decimal to binary. Okay, the number is 10. uh, okay, so if I give 10 as the input, I get 1010 as the output, which is fine. If I give 15, then I get 111, which is the binary representation of this particular number. So that's all. Thank you.